Yeah, hello everyone. Good morning. Am I audible? Can you post on chat if I'm audible? Hello. Yeah, guys, can you post on live chat if I'm audible? Yeah, that's great. So, hope you all are doing good. My name is Akash, and I'm a co-organizer at GDG Cloud Indore. So, we are really excited for this session, and it is one of the most awaited session of this year. So, our today's speaker is Ms Stephanie Wong. She is a developer advocate at Google Cloud. So she'll be taking session on designing networks for high availability and visibility. So this talk will cover best practices for designing networks that are using Google Cloud load balancers. So without any delay, I would like to invite Ms. Stephanie. Over to you, Stephanie.
Thank you so much, Akash. Hope everyone can hear me fine. It's good to be here today, or I guess tonight for me. This is actually the first GDG session that I'm presenting at, so I want to thank Tushar and Akash and the entire GDG Cloud Indore group for inviting me here tonight to present. I'm super excited to be here. I'm glad there's such a big turnout here. As Akash said, I'm a developer advocate at Google Cloud. I work primarily with scalable advocacy. I talk about any GCP product, mostly focusing on online content. So you might be familiar with seeing some of my YouTube videos. I've created series for networking called Networking End-to-End. Lots of content on load balancers in the past. And then I've touched on many other products like our security products and enterprise discussions with some of our internal Googlers as well. So I encourage you to check out more on Medium and YouTube. But for today, I'm here to talk about designing networks for high availability and visibility. This is a topic that I'm fairly passionate about recently, just because it's an exciting topic and we have some new products that have come out in the last year that I want to introduce to you all today. So let's go ahead and get into it. So first, I kind of want to talk about high availability and how to design that into your architectural landscape on GCP. So as you know, modern high traffic websites serve hundreds of thousands, if not millions, of concurrent requests for user and clients, and they're supposed to return the correct text, images, video, application data, whatever it may be, in a very fast and reliable manner, as I'm sure that you are all familiar with building your own applications. Now, the challenge here is that it's difficult to make that happen at scale. It might be something that you can achieve in your dev test environments and maybe in a single region. But what happens when you scale beyond a single zone or region and you really want to reach higher availability to your user base as your application grows in demand, which is a good thing. A huge foundation to making this all possible is load balancing. And I'm more than thrilled to actually dive deeper about this because I think Google Cloud has one of the strongest and most robust load balancers that's software defined out there. So load balancing, if you don't know, is the process of distributing traffic across your networks of servers to ensure that the system never gets overwhelmed and all the requests are handled easily and efficiently. So the load balancer for Google Cloud helps you distribute to multiple regions. It helps distribute load balance resources in either a single or multiple region. You can meet your high availability requirements. You can achieve auto scaling with intelligently designed auto scaling capabilities built into our load balancer. And you can also use our content delivery network as another feature that you can tack on by using our global load balancer. So with the CDN and just the L7 and other load balancers we offer, the whole goal here is so that you can get your content and traffic closest to your end users, and it's built off a system that already can handle millions of queries per second within our network. So given that, which all sounds great, I will admit that it is somewhat difficult to choose and understand some of our load balancing options on Google Cloud. It's kind of difficult to know when to settle and how to settle on a great load balancing architecture that meets your needs and figure out the prerequisites that you need to achieve for the best performance without making too much of a dent in your wallet at the same time. So the easiest way to think about how to decide which load balancer to choose is, are you dealing with external traffic, which is publicly facing traffic that is on the public internet, so anything coming from your end users into your front end servers or web servers, for example, or are you serving internal traffic? So that's anything that resides within your Google Cloud VPC. Maybe you have a load balancer set up for L4 or L7 internal traffic, and that's hitting your databases or backends, and it's only residing within internally facing traffic. So that's one way to decide on the first step of which load balancers to choose from. Another decision point is the type of traffic that you're serving. So are you primarily serving HTTP, HTTPS traffic, SSL, TCP, or UDP? Because we have different load balancers that will serve each of those traffic types. Now, there is the sort of other way to look at the load balancer group of products that we offer is, are they global in nature? Do you want to serve traffic globally to your end users, or is that something that you're planning on doing in the long term? And or is it regional traffic that you're serving? And this is all in conjunction with deciding the type of traffic that you're serving. So you can see here, for global, we have HTTPS, HTTP, SSL, and TCP proxy load balancers. And then for regional, we have network load balancers and our internal layer 4 load balancer as well. So all of our load balancer options fit into these sort of boxes, these various boxes that they sit in. One thing to note is that load balancers at the end of the day are going to be really important to architecting your overall landscape on Google Cloud. It's important across multiple products that we offer. So whether you're running on Google Compute Engine, Google Kubernetes Engine, or even just serving static content on cloud storage, you should consider always putting a load balancer and implementing that at any layer of the stack. Whatever it is you're doing, load balancers can and should be a part of the solution and part of your network architecture. So one of them that I want to focus on today primarily is our HTTP and HTTPS load balancer. And then I'll go ahead and show you how to actually set that up. So before I dive into it, I want to talk about DNS-based load balancers. Now, this is sort of a traditional model of deploying a load balancer either on-premise or in the cloud. It's a topic that usually comes up with developers asking questions about load balancing on Google Cloud, like why don't we use a DNS-based global load balancer as our preferred mechanism? So the challenge with DNS-based load balancing here is you can see from this illustration that with many traditional load balancers that are designed this way, you're going to be running multiple backends in various regions. And that also means that you'll most likely be having to run various DNS servers, DNS records that are pointing to these various regions. So the problem with this is that a lot of things can be outside of your control. So for example, you could have a failure in, say, San Francisco, and you'd have to then update the DNS record potentially. You will probably risk people hitting a stale DNS entry because they don't have the most current DNS records and can't actually access your application. If something were to occur to one backend, in order to reroute requests to the next closest region, you would then have to update the DNS record to point to the IP address of the backend sitting in New York, for example, or Singapore, whatever the next closest region would be. So that's one downside to this approach. There's nothing wrong with necessarily having this approach. It's just not the way that Google has decided to implement our L7 load balancer. We looked at this model and decided that with our global user base, that there was probably a more efficient way to deploy at scale. So this is sort of Google's way of answering and addressing this problem. So this is our layer 7 global load balancer, and it's a really powerful construct. It's the same one that we use for Gmail, YouTube, search, and it's built with scalability and high availability in mind. We built this just because we flat out needed to support our billion-plus user products. So one of the biggest benefits here is that it's software-defined load balancing, and you're able to scale across Google's front-end engines. This is sitting at the L7 layer, and what this allows you to do is actually point any global traffic to a single virtual IP address that's globally accessible. So what that means is that if you're running, let's say, myapp.com, and you have users sitting in California, New York, and Singapore, they will always consistently be able to access the load balancer external IP address, which in this case is 200.1.1.1, and they won't have to access or reach a different external IP address for each backend sitting in their closest region. So the benefit of that is that if one region goes down for whatever reason, network failure, or the backends became unhealthy for any reason, there's no manual intervention on your part that would need to update that stale DNS entry. So that's like a huge benefit there that I think is really highlights a differentiator for Google's load balancer. Yeah, no matter where you are in the world, you're always going to be hitting that same IP address. So behind the scenes, what's happening here, and this is sort of illustrating the example of what happens if one of my instances or backend instances and its groups go down in Singapore. What happens to the user accessing myapp.com? Well, their traffic is redirected to the next closest region sitting in, let's say, US East. Maybe I only have additional servers sitting in US East and US West. Then they would be redirected back directly into US East serving instances. So you can see here in the diagram, like the traffic is going through Google's front end servers, as you can see, and that's able to distribute traffic using something called a waterfall by region algorithm that will be able to understand that they need to redirect traffic to the next closest region. What you get from this is that you just basically get a better user experience, no intervention on your part to make this happen, and you can set up health checks on your instances and auto scaling capabilities so that once it reaches an aggregate CPU utilization, maybe it's completely over provisioned in Singapore, then the traffic will be redirected without you having to go in and make that change yourself. Similarly, if you decide to deploy CDN on top of your load balancer because maybe you want to cache static content or media closest to your end users, you can also use that here too, and it sits parallel to our global load balancer. So in terms of scale and how this works in the back end, the layer 7 HTTPS load balancer can handle millions of queries per second, as I said, and it means that you can deploy backends in different regions around the world and ensure that the system can handle that load. So in this architecture, you can see that there are multiple VMs in an instance group sitting in different regions. This is sort of the best design for creating a highly available network. And the key here is that you have multiple backends that are replications of one another sitting in each region. And you have a front-end load balancer that will send traffic to the closest region. So in this case, Singapore users are hitting the GFE sitting in Singapore, and it's reaching the backends. Let's say the backends become overutilized. Then what happens if there's, let's say like way more queries per second than you had expected because maybe you reach a spike in traffic due to some holiday or shopping event that happens? Then by the waterfall by region algorithm, that'll kick in and it'll automatically spill traffic over to the servers that are sitting in the US West in this case. Or let's see, in this case, it's in US West, correct. So it's going to distribute traffic based on available instances. If you need to add more instances based on load, it will also work in conjunction with what we call auto scaling. So if you set a certain limitation for CPU utilization for your instances, maybe you have a max auto scaling limit of 5 instances, and it'll scale up automatically to 5 instances. Once it hits its utilization maximum for 5 instances, it'll then spill over to the next closest region. So all in all, this is kind of allowing you to implement something that's not only highly scalable and available in one region, but across regions. And then the load balancer acts as another layer that will allow you to have a better user experience overall. Cool. So the data model that this is built off of, this is sort of showing you how you actually build a load balancer on Google Cloud. Like what are the steps involved with deploying a load balancer? So on the left-hand side, you have the internet. This is where your users' traffic is coming in from. The first thing is going to be a global forwarding rule. So how are you going to forward these requests to myapp.com? Which backends is it supposed to reach? It will then hit a target proxy, and this includes a URL map. So this is specifically in the case that you might want to direct specific traffic to a backend if someone is accessing myapp.com/buymycoolstuff. Maybe you redirect it to your shopping application or cart application specifically. So you'll be able to build URL, host, path, and rules that will direct traffic based on URLs. And then once that's created, you will then direct that to a backend service, which will tell the traffic to go to the specific backend managed instance group. So backend services are essentially what we call managed instance groups. I'll show you what that looks like in the console, but effectively you can consider managed instance groups like a scalable, highly available way to run your backends. So that could be a web server that you're trying to get to, or it could be the shopping application that you're running, and you would deploy those in replicated instances that are managed in an instance group. And then lastly, on the right-hand side are firewall rules. Of course, you need to create firewall rules to allow traffic from specific IP ranges into your application and deny any kind of unwanted traffic otherwise. So let's run through some of the features that are tied to our L7 load balancer. So you have a single global Anycast VIP, as I said, and this can be either IPv4 or IPv6 for a load balancer, and it can be running globally across regions. These are processes that run at Google's edge. As I said, they're highly scalable, and we use this for things like our search engine. You have worldwide capacity with our global load balancer, and you also have cross-region failover and failback. So you might have instances running at all regions, but let's say if your backends in Europe go down, then the load balancer will know that it's not in commission, and it can redirect traffic to the next closest region with backends. The load balancer also has fast auto scaling. So this is actually an example of how we can also protect you from potential DDoS attacks. We have the capabilities where the load balancer can instantaneously auto scale itself so that it can protect you from any kind of DDoS potential attacks there. Single point to apply global policies is something you can do as well. So we talked about URL mapping, but you can also apply various security policies. So for example, we have a security product called Cloud Armor that you can allow or block IP blocks to the load balancer, and that's something that you can use in conjunction with this. And I already talked about how it can handle a large amount of load, over 1 million plus queries per second. All right, so just to show you what that looks like. So I'm in the console right now. I just want to show you kind of like, give you a better idea of the managed instance groups, as I mentioned. So before you can create a load balancer, you want to deploy your backends in a managed instance group. They're basically managed replicated instances with the same image that you deploy on all of them. Now, one way to do that is to actually create a Google Compute Engine template. So the template is essentially just a configuration template that you can deploy once and then create managed instance groups based off that template configuration. So just to show you what that would look like, I already have one created for my load balancer backends. It's called Web Server. I've deployed a Mandelbrot server, and it's basically doing large computational tasks. And I deployed that in 2 managed instance groups, region 1 and region 2. And then I put a load balancer in front of that. But just to show you what creating a template looks like, you essentially specify the name of the template, the machine type, or you're probably familiar with these, and one standard. You have memory optimized, the type of image that you want to deploy on the boot disk, any kind of specific service account, firewall rules to allow HTTP traffic, and then you can select the network that it will reside in. So in my case, I've created test networks for my load balancer, and any other tags that you want to. You can assign an ephemeral or public IP address to it. And network service tier is basically whether you want to utilize Google's network backbone, which will give you higher throughput, or you can use standard internet service providers as well. So once you create the template, you'd be able to go to Manage Instance Group, As you can see here, I've already created 2 managed instance groups based off the web server template that I had originally created. And managed instance group, as I said, this is a way for you to have better redundancy across zones. So they're identical VMs that you deploy across zones in a region, and then you could create more than one so that you have one in multiple regions, and you would put the load balancer in front of that. So when you create a new managed instance group, again, you can select either single zone or multiple zones that it's deployed across. You can select the template that we just created and allow either auto scaling on or off. Auto scaling essentially allows you to determine whether you want to allow the managed instance group to automatically scale the number of instances based on a metric like CPU utilization. The default is 60%, or you can add a different metric. HTTP load balancing utilization for the load balancer, or there's some other stack driver monitoring metrics that you can implement. Cooldown period essentially is used for connection draining, so users don't experience disruption. So as you scale down to the number of instances when demand drops, it will intelligently wait 60 seconds to drain connections from that backend before it takes that instance out of the group, so that your users don't experience a very blatant cutoff period. Minimum and maximum number of instances are used for auto scaling. So of course you don't want to wake up to 100 scaled instances, which might hurt your wallet. So this is a way for you to specify the exact number of instances that you want in the instance group. I always recommend starting with 2 minimum, just so that you have higher availability within your managed instance group. Having 1 is fine if that is, if that's your preferred, just for the amount of traffic that you expect to have, or maybe it's for cost optimization, but 2 would be a good number to have as a minimum. And then auto healing, there is a health check that you can implement. So basic is just doing an HTTP check on port 80 with every 60 seconds. And then you would just create it, and it would start deploying the instances immediately from when you click that button, and it will show up in VM Instances tab here. So you can see here, I've already deployed 3 instances in each region based off that template that are accessible here, that are computing Mandelbrot. And then as we go to create the load balancer, that would be the next step. So we've already completed the prerequisites. We've set up our backend instances. Now we want to create our load balancer. So I've already created one based off those 2 different managed instance groups. This is the load balancer called WebMap. But in the case that I want to create a new one, you basically have the choice depending on the type of traffic you're serving. Here, in our case, we created HTTPS load balancer. You can start configuration here and choose from internet or maybe between VMs. But in this case, we're doing publicly facing. And backend configuration, we've already created the managed instance group. You just need to create the backend service. I've already created one called web service, but you could create a new one and specify the instance group that it's going to point to, or maybe it's pointing to a GKE backend, the protocol that it's using, or you can create a new backend instance group from here as well. We wouldn't do that because we already created one. Host and path rules. This is sort of what I was talking about, URL mapping. So for example, www.myapp.com would hit our homepage, and perhaps I would have myapp.com, and on the next, it would be /buymycoolstuff. And you would create another backend service that hits a specific backend managed instance group. Front-end configuration is basically setting up the actual load balancer front end. So you would give the load balancer a name. Again, the protocol is HTTP in our case. Premium tier is the network service tier. Premium is recommended because this is using Google's backbone, meaning that you're using Google's network, and you would be able to have more reliable and higher throughput network as opposed to having higher number of hops between internet service providers. So it's kind of up to you, depending on what kind of throughput you want and the affordability of it. But obviously, I think if you want the best performance, it would be premium. IP version, depending on the type of traffic IPs that you are already using. And then you have a chance to review and finalize and create there. It will take a few minutes. I already created a load balancer here that I'll go ahead and show you. So here I've created web map. It's HTTP. It gives us an external IP address. It's using premium. And the backends are listed here that I've already connected. Web server region 1 and web server region 2. One is sitting in US Central and one is sitting in US East. It gives you the health check information. 3 out of 3 instances in each group are healthy. Haven't configured auto scaling in this specifically. I have specified a maximum of 10 requests per second here. And what I've done is, this is sort of to show you, it will give you a visual topology information about traffic flow. So you'll be able to see any traffic that has hit either web server region 1 or 2 in the last 12 hours or a day. And you can kind of see from there, but I'll show you in just a moment as well another way that you can visualize traffic flow. Caching is an option in case you already enabled Cloud CDN, and you'll be able to see whether or not you can add a CDN origin for any kind of cache content closest to your end users. So that's sort of how you would set up a load balancer. One other way to do this is actually through the G-Cloud CLI or SDK as well. You can definitely do that through here. But it's nice having the GUI interface as just an option. All right, so just going back to the family of load balancer products, it's not just the HTTP load balancer that will provide you with a highly available network. It's common practice to load balance requests received from external sources like web or mobile clients, and then also using internal load balancers for different services or tiers within your application. And that will, of course, increase resilience and flexibility. We provide internal layer 4 and layer 7 load balancing for this purpose. So just make sure that you attempt and try to implement load balancing at all layers of the stack. Also, if your app is running on GCE or GKE, you can choose the most appropriate type of load balancer depending on the type, source, and other aspects of the traffic. Yeah, so take a look at what is the most appropriate for your architecture. Alternatively, we also have other managed services like, of course, App Engine and Cloud Run, and they already handle load balancing for your traffic. So you don't have to set up a load balancer specifically for that, but they will have auto scaling capabilities and scale down to 0 for Cloud Run as well. So just to switch topics just a little bit into the visibility realm, this is something that I wanted to introduce because this is a Network Intelligence Center is something we came out with just within the last year. And it's pretty exciting because I think this is a huge differentiator for Google Cloud. What it is it's a comprehensive monitoring, visibility, and optimization tool. It uses AI and ML infrastructure capability, and it's kind of meant to make your migration from either on-prem or from cloud to cloud a lot easier by giving you visibility across your environments, whether that's hybrid or across multiple clouds, and give you a little bit more insight so you can plan your network topologies better. So I'm sure many of you already have some networking backgrounds, and you might have run into outages at some point. Usually, whenever there is a network problem or a problem within your network topology, whether it's on-prem or maybe connectivity between on-prem to the cloud, network is usually the first thing that you're going to point at and consider it guilty from the get-go. So the whole goal of Network Intelligence Center is to give you more insight into configuration changes. So if you're asking questions like, why is my application performance not doing well? I'm not able to reach the right backend. This tool should give you a little bit more troubleshooting and visualization so you can pinpoint exact problem and exact cause of that configuration or performance issue. So these are just things that we hear from our customers and users. Usually within the last several years, many people have said there's too many tools out there. There's sort of a lack of comprehensive monitoring and visibility or diagnostic tools for networking. So when you come to the cloud, there's sort of a lack of cloud native capabilities that give you a similar experience to what you have on premise. Then you end up using a plethora of networking visibility troubleshooting tools and different tools for planning, different tools for optimizations, etc. And then on top of that, it's kind of hard to diagnose across environments. You end up setting up VPNs from different vendors. You might end up connecting different interconnects or partner interconnects. So resolving connectivity issues between on-premise and different clouds takes a really long time. On top of that, there's a lack of real-time performance. So for example, if you're running in different regions, it's difficult to find out whether the performance issue in a zone is due to an outage that occurred in Google's infrastructure, or whether it's because the application in your VPC had deteriorated, or maybe your configuration had caused an unintended consequence. So for example, if I was doing database backups to do different regions and it ends up going to another region and I didn't intend for that to happen, and then my egress costs go up. So we need a way to have real-time information to diagnose these types of issues. The other question that we get asked a lot is like, what happens if you make a configuration change in your network topology? So the point of the Network Intelligence Center is to help you answer questions like, what's your current packet loss? What's your current latency? What's your current bandwidth? So these sort of network parameters will make giving you more information about performance of your network and your applications. For example, if you make a change in routing or load balancer backend policy, you want to know the impact of the change and also know how to optimize them. So yeah, overall, it's just difficult to have a holistic view between DevOps and Cloud Ops and Network Ops. So this is sort of here to help you get your teams working better together and then confidently tell your end users that you have the intended behavior that you expect, and you can optimize configuration so you can strengthen your SLIs that you can offer for your end users. So here is sort of a user's journey for using something like Network Intelligence Center. First off, you want to be able to surface the problems and troubleshoot failures, whether they're static configurations or dynamic reachability tests. Here, what we're doing is making recommendations and allowing you to understand when you should fix things within your network configuration. The system should eventually, I think we're not here yet, but eventually on the roadmap for Network Intelligence Center, they want to build in the capability to utilize AI and ML to monitor your configuration changes, monitor your traffic, and then based on that, be able to make recommendations before you put it into production. So sort of like act like a safe sandbox environment where you can validate your configuration changes and know exactly what the result will be, and then actually be able to provide you with new recommendations for how you can continue to optimize your network. Then once it provides you with predictive information about that, you can either accept or reject those recommendations and identify more cost-saving opportunities that you can change and new configurations that you can implement. So there are a few different modules that are currently in Network Intelligence Center, and there's more that is being built. The first one is connectivity test. So this is basically based on a platform within Google called Reachability. And the point of connectivity test is to provide you connectivity or reachability information. So it kind of ensures connectivity exists, and you can then prevent outages using on-demand troubleshooting tools. And then the second one is called network topology. And that's sort of a visualization of your network topology. And then thirdly is performance dashboard, which gives you SLIs and SLOs based on the entire health of your network. And then also Firewall insights will give you the ability to identify shadowed or misconfigured firewall rules. So I'll go a little bit deeper into each of these. So the first one, connectivity test. This enables you to evaluate connectivity to and from Google's resources in your VPC by performing static analysis of your resource configurations. You can either check connectivity between, let's say, 2 VMs within your project, or maybe you want to check between VPC network and the public internet, or check between VPC and your on-premise network. So it gives you the ability to create tests and constantly check the configuration. And then you can therefore find out whether you have inconsistent configurations that you didn't intend for. Maybe you have obsolete configurations due to different changes that happened, or any errors that might come up. So the way that this works in the backend is a model is created of your entire system, every configuration that's in your organization within GCP. And then the model essentially runs 4 tuples that will add as source and destination, but for your connectivity tests. And the system will run basically from source and destination a simulation. So we create different path traces based on your configuration and run a simulation through that. Based on what we detect, we can tell you whether your connectivity is either up or not. So it's essentially a static configuration model-based analysis. One key thing to note is that don't get confused with Cloud Trace, which is Stack Driver Trace. The difference between this and Stack Driver Trace is that this is more for, using a performance analysis based on your current configuration setup. It doesn't actually send a packet through the data plane. It's just used to show you where packets are dropped due to firewall rule or routing misconfigurations. Stack Driver Trace, on the other hand, is more great for in-depth latency reports due to like service degradations, and it kind of helps you identify performance bottlenecks based on actual logs. So it's actually based on actual latency data. This one here for connectivity tests is more so performing a simulation between source and destination. So here is an example architecture that I've deployed in my GCP project. We have backend sitting in US East, which is Ohio, and then we have a backend sitting in US Central, which is Texas. And I have set up 2 cloud routers, so I can set up dynamic routing in between them, which is, in other words, a BGP session. And then I also set up a VPN gateway between the 2. So here's just an example, like, okay, this took a several amount of steps to set this up. I want to make sure that there is actual verified connectivity between the 2 servers, and it's actually working as intended. It's actually going through the VPN gateway and using dynamic routing. So let me show you what we can do here with connectivity tests. So let's go ahead and create a connectivity test. So in this case, I'll say this is my BGP test. It's going to be a ping test. I'm going to use ICMP protocol. And here you have the option of choosing a VM or an IP address as source or destination. In my case, I'm going to choose VM. I'm going to do Ohio server. And I will choose a VM again for destination, Texas server. You have to specify whether it's in a different project, but in my case, it's in the same project. And I'll click create. So right now, it's just going to create the test and run through it once you initiate it here. So here you can see it's unreachable. Maybe that was your intended. Maybe it's your intention that you want the test to be unreachable. But in my case, I want it to be reachable. So let's go ahead and view the details. You can see here that it's really nice because it gives you a visual understanding of where traffic is coming from and heading to. In my case, the source is VM instance, which is Ohio server. So far, green means the packet is able to traverse through the egress firewall rule. It does hit a dynamic router through the VPN tunnel gateway on the east, enters the VPN gateway on the central, and then it hits a subnet route. Now, what happens here is that it's unable to reach the destination VM server in Texas due to a default ingress firewall rule that is either not being applied or it's being applied. So what we want to do here is determine what the issue is. So I can actually just go ahead and straight to my firewall rules and check it out. If I kind of filter down to the ones that I know apply to that instance, I can see here that right now my allow ingress firewall rule to the Texas VPC is currently disabled, as you can see here. So what I want to do here is, it's nice. You can go directly and edit this incoming ICMP traffic ingress rule for the Texas VPC and change it back to enabled. Let's go ahead and save that. Once that's saved, let's go back to the connectivity test once more and rerun the test. Okay, so it successfully reran and now it's reachable, which means that we have implemented the correct configuration change, which happened to be the firewall rule. You can see here the packet could be delivered based on the modeled simulation test, and it's able to reach the destination Texas server. So this is really great just for doing ad hoc tests. Before you implement something in production, for example, it's a really easy way to see clearly whether or not connectivity occurs as intended or it's not reachable. And maybe that's your intention, as I said. So going back here, that's connectivity test. Let's go ahead and talk about network topology. So network topology is another module in Network Intelligence Center that helps you visualize your network so that you can monitor your network health easily. So it's combining configuration information with real-time operational data in a single view. And that makes it easier to understand networking relationships between various workloads on Google Cloud, their current state, like traffic paths and throughput between VM instances. And it kind of lays it out in this graphical format. It's a nice visual format that you can see within the console. And you have nodes and lines representing entities and connections in your network. How it works in the backend is that it collects real-time telemetry data and configuration data from our infrastructure to visualize your resources. So it's really just capturing information like metrics and logs to kind of infer the relationship between the different resources within your GCP environment. And it can work within a project or multiple projects. After collecting each element, it then combines them all into this graphical interface that you can see. So the benefit here is that you can easily understand the topology of your deployments in a visual format, and you don't really have to do any kind of additional configuration to use the tool. You don't need to set up like additional multiple logs or use third-party tools to understand your infrastructure. It just does that for you. That way, you can then analyze the performance of your network. You can drill down, see more metrics, and do some filtering to figure out how everything is in relation to one another. It's really nice for just kind of like quickly diagnosing and troubleshooting issues. All right, so just to show you what that looks like in this environment, as you can see, it's a very nice, clean way of seeing how everything interacts with one another. Here I have my external load balancer laid out. You can drill in. It's the front end that I had deployed just now called web map, and it's pointing at US Central. There's an instance group that I showed you earlier, web server region 1, and then US East. And now, as you can see, it's a little hard to see in this case because it's pointing at additional services that are sitting in various VPCs that I've deployed in this project. So one thing to make it a little bit simpler is you can search. The search capability gives you the option to search for a specific instance or search for a specific load balancer and then drill down into exactly what you're searching for. So in my case, let's just drill down to the web map load balancer, and then I can much more clearly see the specific backends that are related to and are accepting traffic from web map. And then you have the option to filter here as well. And then on the bottom here, what's nice is you have a timeline so that you can actually see the evolution of topology changes. I don't have a long history here, but I can see that originally I had only deployed in US Central, and then over time I deployed in another region. So it's kind of nice to see the changes. Maybe you had another user make changes, and you'd be able to see the topology change over time. And then another use case for this is like during migration, it helps you monitor the state of your deployments as you migrate, thus kind of providing better visibility into your migration process and letting you track it by looking at the evolution over time. One thing to also note is that you can do this at the organizational level, not just project level. So if you want to see view of multiple projects, that's one way of getting the network topology of the entire organization and all the teams that are making deployments within GCP. So just use cases for network topology include, monitoring your network, of course, proactively detecting problem areas. Can you truly say with confidence that your users in Asia are being served through the bouncer to the backend instances in Asia? You can also do network troubleshooting. You can do like root cause analysis of different events maybe see the impact of different changes over time. You can also do architecture optimization. It's clear that you can have a visual understanding of your architecture and the network topology and really understand clearly how you can optimize for it. Maybe you can see what's contributing to your egress costs. Can this be changed? Can this be optimized? How can we improve on costs there? And then track workload migration. Again, as I said, you can use this tool so you can see how things have progressed over time as you migrate VMs into the cloud. And then lastly, if you have any kind of like regulatory compliance needs, like SOC audit support, this could be a good way for you to showcase evidence pointing to how your topology has changed for SOC audit reports without having to export everything to a third-party tool. So the next module within Network Intelligence Center is Firewall Insights. This gives you better visibility into firewall rules and how changes might impact traffic behavior. That way you can kind of tighten up your security boundaries and detect any kind of abnormal traffic patterns. That way, and you can also safely optimize for configuration, and you get reports and information on firewalls and how they're being used, how often they're being hit or not hit. And the whole reason why we built this is that it can get very complex. Like if you had thousands of firewall rules and you had them all in your console, it's really difficult to understand what's being used, what's actually being hit, what firewall rules are shadowing other firewall rules. Yeah, as you can imagine, massive volume of firewall rules is difficult to understand. You might have over-granting or like very broad firewall rules, and that means it's a security risk, right? Or you might have under-granting rules, like maybe it's not, maybe it's so restrictive that it's insufficient to drop traffic. And then maybe you have outdated rules, maybe you have human errors, maybe some of your developers have created rules that have errors in them, or maybe it's just unmaintainable. It's just too much to maintain over time. So the whole point of Firewall Insights is so that you can kind of manage firewall rules more easily. You get metrics for tracking utilization. You can see the impact of changes, and then just verify that the rules are being used in the intended way. So let me just go ahead and show you what that looks like. There are 3 different types of rules that you can monitor. The first one is shadowed firewall rules. That means that a shadowed rule is basically a firewall rule that is being shadowed by another rule that's more encompassing. For example, it could either be by priority level, or maybe it's allowing traffic from a wider IP address range, for example. So that's shadowed rules. And then for allow rules with no hits is basically any allow rules, for example, allow ingress rule that has not been hit in the past 6 weeks. And this is provided by log data. So you have to make sure you create your firewall rules with logging enabled. And it's only accurate if that's been enabled for the last 6 weeks. Deny rules with hits are, as explained in the title, deny, it's any rules that are deny and they have been hit. So anything that's been hit, that's a deny rule in the last 24 hours will be surfaced here. And then you can check to verify that the dropped packets are expected due to maybe security protections, or if they're unexpected, it might be due to a misconfiguration. The hit count number is accurate only if you had the logging enabled in the last 24 hours. All right, so let's give you an idea of what that looks like. So here I have another project, and this is our list of VMs that we've deployed. So let's just say that I'm accessing VM1, I do a ping to VM2, and it's not working. I'm getting any kind of packets being sent. So one thing that you can do is look at the network details for that VM to try to figure out why that's not working. Maybe it's vice versa. And you can see here any kind of firewall rules that exist, anything that has hits or when the last hit was. But if you do want to explore further, just go ahead and go to the Firewall Insights page in Network Intelligence Center, and you can see here the 3 different cards showing the buckets. So shadowed rules, as I said, are any kind of over-encompassing rules that are shadowing another firewall rule. It's taking priority. So in this case, a rule can either be shadowed by 1 firewall rule or 2 firewall rules, or combination of firewall rules. So in this case, this firewall rule is being shadowed. it's supposed to allow traffic to this IP range, from this IP range for TCP, HTTP, and HTTPS traffic. In this case, it's being shadowed by two different rules, one that's denying HTTP and one that's denying HTTPS traffic. So if you're able to see this very easily in this format, you can go ahead and just go directly to the deny rule here and either enable or disable the rule. So that's a really easy way of seeing shadowed rules that are misaligned. And then another feature is the allow rules with no hit. As I said, any allow rules that haven't been hit in the last 6 weeks. So this is really good for you to be able to clean up your firewall rules. Maybe you have a lot that just aren't being used. For example, if I look at one of them, we see here that somebody forgot to clean up this firewall rule that's allowing traffic to our web app 1 instance from the public internet. And it just hasn't been used in the last 6 weeks. So you might as well just delete it. And then for the last section of Firewall Insights, we have deny rules with hit. So these are deny rules that you've implemented either to protect your network, and this is the hit count. So if I want to look at one of them, let's say deny web traffic has a hit count of 3,100. It brings you over to our logs, and you're able to see and drill down on any kind of logged data that showcases that the firewall rule has been hit. So you can pretty much drill down on the payload here, the JSON payload, and see information about the connection, the instance that it was applied to, whoops, and perhaps the remote location that it came from. So you can kind of do troubleshooting and understand, why is this deny rule being hit so many times, and is that the intended behavior? Is it working effectively? We also have performance dashboard. This is when performance issues arrive, you have a better understanding of seeing packet loss and round trip time for latency. And it's a dashboard that kind of collects information from all the projects you have. And there's no manual setup. You just get this built into it. And you can get some real-time information about packet loss and latency metrics so that you can kind of serve better SLIs for your users. So I'll just quickly show you what that looks like. If I go back to Network Intelligence Center, Performance Dashboard. So you have packet loss metrics over time, VM to VM packet loss, and you also have latency metrics over time. And you can see in a heat map, median latency between zone pairs. So any instances that you have any kind of round trip time latency averages between the zones, and color is indicated by this heat map. Same thing for packet loss. So those were the 3 or 4 different modules that I've showed you. I know I want to leave some time for questions, but the key takeaways here in terms of like high availability and the Network Intelligence Center is hopefully I kind of equip you with some options to start implementing and building a highly scalable and resilient architecture at all layers of the stack. You want to be able to have more visibility into your topology and diagnose misconfigurations using Network Intelligence Center. So the call to action for you is to just try setting up managed instance groups using instance templates and implement load balancing using auto scaling across regions for higher availability. And then, of course, proactively utilize the Network Intelligence Center so you can see all the configuration changes and network topology and be a little bit more proactive about performance in your network. So that's a wrap. Again, a lot of this information I've either built through articles or videos. So definitely follow me on Twitter at Swangful or medium.com/@Swangful. And here's a bit.ly link for any kind of YouTube videos that I'm in, and I update that pretty frequently. So thanks so much for joining. I guess I'll kick it back to Akash.
Yeah. So we have few questions lined up. So I'll read the questions and you can answer those.
Okay, sure.
Okay. So just a second. So first question is there any internal HTTPS load balancer also? So last I heard it was in beta.
Yes, the answer to that is yes. I believe it might still be in beta, but that is available. I'll have to double check on whether that's GA yet. But the last time I talked to the PMs, yes, it's available in terms of potentially being in beta.
Okay. So next question is, what effect does the selected cloud region for our project has on the configured load balancer?
Selected cloud region for the load balancer. That's just where the load balancer front end resides. You can have it be serving global traffic. But there are regional load balancer options, for example. If you deploy the network load balancer, that is a regional load balancer. So you would want to deploy that in the same region as your backends, in that case, if you're serving TCP, UDP traffic, depending on the type of traffic that you're serving. For the HTTPS load balancer, that should serve global traffic.
All right. Okay. So next question is, what is the difference between HTTP and network load balancer?
Sure. Let me actually see if I can bring that up really quick. Sorry, 1 second. I don't know if you can still see this. Yes, you can.
Yeah, we can see that.
Okay, great. So yeah, as I said, network load balancer is regional. So that's one differentiation, and it load balances for TCP and UDP traffic, so it doesn't look at L7. Client IP is preserved. You have client access that you can control via firewall rules, and there's different hashing mechanisms that are implemented, and you can still have health checks and things like that. You still have the high performance, but primarily speaking, it's TCP and UDP traffic.
Okay. So next question is, does Cloud Run supports network load balancing?
That's a great question. I believe, well, so I don't know the exact answer to that. I think that because it is already built in as a feature for Cloud Run, I don't know that you can configure the network load balancer specifically for Cloud Run because it's a managed service. So that's my short answer.
Okay. So next question is, how Google is managing servers, how servers are being auto-scaled, and what is the CDN behind that?
Yeah, so there's different options that you have for configuring auto scaling, whether that's based on the load balancer HTTP for utilization, or you can base it off of the CPU utilization of the aggregate number of instances that you have in a managed instance group. So if it hits, for example, 60 or 80% aggregate overall CPU utilization for the servers that you have at the moment, whether that's 1 or 2 servers, whatever the minimum servers that you have at that given moment, then it'll kick into effect to auto scale to add another instance. And then once it drops back down to a lower CPU utilization, you can also have it reduce the number of instances back down.
Okay.
So yeah.
So another question, can we have multiple connectivity tests at a single go? So it's like holistic connectivity test rather than individual test.
So it looks like right now you would have to build multiple connectivity tests, and you can have them all listed out. So for example, in my case, I could create another test for the traffic going from Texas to Ohio, and then another test from Ohio to Texas. But you would have to build 2 different tests for each bidirection, if that makes sense. I'm not sure what the roadmap is for seeing sort of like a multiple channel connectivity test, but at the moment it's like you do have to create it individually for each direction, source and destination.
Okay. So next question is, what is the difference between vertex and port-based routing?
Vertex and port-based routing, that I'm actually not sure of. Port-based routing, I think, is self-explanatory in terms of like routing to specific port and traffic type. Vertex, I actually haven't heard of that, so I'm not 100% sure, but ping me after and I can find the answer for you or tweet at me.
Yeah, so that's it from question side. So thank you for your session from GDG Cloud Indore. It's always great to have such a speaker like you here. So thank you so much, and thank you everyone for joining us.
Thank you so much, everyone. Thanks for having me. I had a great time.
Thank you.
See you.
See you.